Welcome back to linear algebra. So a fun one to start with for the day. What we got going on in Anki? 9? Suppose that A is an m by n matrix and X is a column matrix, a vector n by 1. Express AX as a linear combination of the column vectors of A. Oh man. Okay. I think it's gonna be 1 or x1 times column vector of A, which is just gonna be A1 1, A2 1, A3 1, dot dot dot, AM1 plus x2 column vector times the column vector A21, A22, dot dot dot, N2, no, AN2, no, yes, AN2, so A12, A22, AN2, dot dot plus dot 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 plus xn times column vector A1 M, no, AM1, no, AMN, no, what the hell, A1N, yes, A1N, A2N, dot dot dot, AMN. Okay. Assuming A and B have the appropriate sizes, how might you compute the jth column vector and ith row vector of AB without computing the entire product? How might you compute the jth column vector? You take the and the ith row vector. To find the jth column vector, you're gonna take the jth column from B and multiply A times that column vector, and to find the row vector, the ith row vector, you're going to take the ith row vector of A and times it by B. All right. What is the row column rule for computing A, B sub ij? You multiply I from A and J from B, row I from A and J, column J from B to find AB ij. Well, we got to sum the products, but yeah. What is meant by a solution of a linear system in the unknowns x1, x2, dot dot xn by a solution? It's basically if you plug in those values for the unknowns, then it results in a true statement. Sequence of numbers S1, S2, Sn for which substitution makes the equation true. True statement, true. Is that good? What is the size of an augmented matrix of a linear system of m equations and unknowns? The size is mxn. Oh shoot, no it's not. It said augmented matrix of a linear. What is the size of the augmented matrix of a linear system of m equations? It's m rows and n columns plus 1, so we missed that. Okay. What is a matrix? A matrix is a rectangular array of numbers. What are the coefficient matrix and augmented matrix of a linear system AX equals B? The coefficient matrix, I believe, is just A. The augmented matrix is going to be AB. Yeah. What is a square matrix of order n? It's an n by n matrix. what is the column row expansion of matrix product AB? Column row expansion, so you're going to take the column of first column of A, it's like C1 times R1, row 1 of B, plus C2 R2 plus dot 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 plus CN RN, where C are column vectors of A and row R are row vectors of B. All right, good. There you go. Happy? Are you happy? All right. I'm going to grade what I did yesterday, and we'll be back after that. All right, guys, that's a first. We just spent the whole time working basically on one problem I got wrong, trying to figure it out. This is the one I was stuck on yesterday. So I proved it at the end of the last video, but that ends up actually only being true for n greater than or equal to 0, or only is a proof that works for that. So we needed to show that for n is less than 0, that the proof works, because the inverse and negative powers for matrices are different, so we got to do a different proof, but it's gonna be the same thing basically. We're trying to prove this. We say that negative m is a negative integer, so we substitute that in. Define the matrix. This is definition of a matrix to the negative power. You can pull the -1 in and times it by that many times. So this. Then we're gonna just do basically what we did up here, but I'm gonna do this tomorrow. This is theorem 1.4.7 here. It's I didn't want to prove it again, essentially, because it was kind of not that related, just that we need to know that you can distribute the -1 to the scalar and to the matrix. Then what we're going to do is finish this tomorrow. So yeah, this is a proof, and yet it wasn't even in the prove it section, working with proofs, so that's kind of annoying, but good practice, I guess, learning that you needed when you're doing this stuff. Like, there's a difference between proofs with positive powers for matrices and negative powers. So that's it for today. Talk to you tomorrow. See ya.